So years ago, LA Fitness opened up a location down here at the end of Washington, right here in Royal Oak. And they had a little membership drive. They're trying to get people to sign up. And they had a couple different offers. One of them, you could spend $250 to sign up and then pay $55 a month. Another one was to pay $350 to sign up and pay $45 a month. Now, if you're looking for this in amongst your notes, you don't have this one. I'm just going to kind of go through this a little bit quickly, try and help you out with where we're going in this section. What are we looking for? Now, both of these represent, equations of how much money you're going to spend over time. So if you're trying to decide, well, which one of these do I want to be in, what would you consider? What would you look for?
Break-even point?
Yeah, the break-even point. Where is the break-even point?
At the 10.
Yeah, right there. At 10 months. That's the break-even point. Now, a little bit of reminder here. These equations are of the form y equals b plus mx or mx plus b. Can you tell which one's which? Which one should I color orange? The top one or the bottom one? Which one do you think? Top one. You've got a higher intercept and a more gradual slope, so that's going to be the bottom or the top one here. So like this. And the other one, of course, is the bottom one. A smaller y-intercept, but a steeper slope. So over time, these two coincide after 10 months. After 10 months, you're spending the same amount for each of these. Which one do you want to be in if you're going to be in there for the long term? You want to be in
The blue.
the blue? I'd say
Sorry.
the orange. Yeah, I'd say the orange because eventually this is going to be cheaper. You're saving $10 a month, and after 10 months, you've eaten up that extra $100 you had to spend. So, all right. In section 10.1, we're going to be looking for these types of points. Where do they overlap? In this case, the point is at 10 and 800. So after 10 months, you're spending $800 with either plan. But let's actually look at the problems that we have on our handout and work through those things there. So we're going to be solving systems of equations. And one thing we're going to look to see is whether or not our systems of equations are consistent. Now, there's a lot of ways you can solve your system of equations. You're going to learn more ways to solve a system of equations in this class than you ever thought possible. Let's find, there it is. So here we go. One way to solve a system of equations is by graphing. Now, it's really nice if you have this on Desmos because then you can do magic like, I don't know, this. Click that and wow, that looks like our solution, right? So it looks like 5 and 4. So let's put that down here. Let's see if 5 and 4 is the solution. 5 and 4. How can I prove that I actually got the right solution from Desmos there? Ellie?
You can plug in your intercept point into the top equation, and it's easier
Okay.
than plugging it into the bottom.
Well, do you have to just plug it into one, or do you have to plug it into both?
You have to put it into both.
It's got to work in both of them. So, yeah. So it's going to be x minus 5 minus 4 equals 1. So that works. Let's try it in the below equation. So it's going to be 4 times 5 plus 3 times 4. Does that equal 32? Well, let's find out that as well. 5 and 4. And 20 plus 12 is 32. So it works in both. Because it works in both, it is a solution. And if a problem has at least one solution, then it's called consistent. So we've got a consistent set of equations there. That's one of 3 different generic types of things that can happen when you're working with a system of equations. What else can happen? Let's take a look at the next one. So we'll shut these two graphs off. I've got x plus y equals 9. Looks okay there. And then 2x plus 2y equals 18. So let's turn on that graph. And, oh, wait a minute. It didn't graph anything. Or did it? What's happening with this second equation when I try and graph it? Yeah, it's the same as the first equation. In fact, if you look at this, can you see the relationship between these two equations? The second one is just twice the first one, right? So they're essentially the same equation, even though they look a little bit different. Now, if you have two graphs that represent the same equation, then your system of equations is said to be dependent. So this is a dependent system. Okay, so we got consistent and dependent. All right. Question for you. Consistent system of equations means there's at least one solution. Is this system of equations, is that consistent as well? Do these lines cross each other or touch each other at least one place? Yeah. So this would be consistent. Yes. Consistent and dependent. Now, if you're not dependent, then what are you?
Independent.
Independent, yes. So up here, because these two lines are different, I would say that this one is independent and consistent. That's how I would characterize that one. Let's look at one other generic type of thing that can happen, and that's illustrated with this last one. By the way, eventually what we're going to do with our dependent system of equations is this. We're going to characterize our solutions in a parametric way. So what's that mean? Well, my solutions to this system of equations generically have the form of x and y, but what if I solved for y here? What would I get? If I got y by itself, I moved the x, what would I get for y?
Equals 9 minus x.
9 minus x. So that's a parametric version of your solution. If you put in different values for x, you get different values for y. But all of them should lie on that same straight line. So let me highlight this little spot right here. And as I vary the values of s, I used s instead of x. Works out better. As I vary this, what happens to the point on our line? Well, it moves up and down, but it stays on the line. So you're, in your own way, you're able to describe all the different solutions to this equation just by choosing different values of s. So you are going to have to do that moving forward. Let's shut all this down and look at this last one. 2x minus 3y equals negative 3, and 14x minus 21y equals 7. Is this system of equations consistent or inconsistent? Inconsistent. Why? They're parallel. They don't touch each other. There's no solution. So in that case, we've got an inconsistent system of equations. So inconsistent. How about is it dependent or independent? What do you think?
Independent.
I got to vote for independent. Good. Why independent? Yeah, you got different lines. Nice. Now, there's a lot of different ways you can solve your system of equations, but sometimes, probably more in a Math 1150 class than maybe this one, but sometimes I'll give equations or a problem like this and ask you to solve. Now, eventually, we're going to discuss substitution, addition, Cramer's rule, inverse matrices, Gaussian elimination. There's a lot of things headed your way. But if I asked you to solve this, what would you do? What would you tell me? This is supposed to be one where I'm going to give this button some love. All right? Prove me right. What's the solution here? And what's the coordinates of that intersection? -8 and 2. Wow. There's your answer. Don't forget that ultimately what we're looking for is where those two lines cross each other. Thank you, Robert. So that's at -8 and 2. And to prove that you got it correct, what you could do is plug it into both of these and make sure that it works. So that would be 3 times -8 plus 2. -24 plus 2 is -22. So that works. What else could you do? Well, let's see, I guess we got to check it the other way too. -2 or -8 minus 2 times 2. -8 minus 4 is -12. So that one works. It works in both of these. So it's a solution. Yay. Now you're not always going to be lucky enough to have a nice graph like this that you can work with. So there's other ways you can solve a system of equations. Let's see if we can't do one of them right here. One of the ways you could solve a system of equations would be the substitution. Substitution. And what am I going to do there? I'm going to move one of these variables to the other side to get one of them by itself. And for my eye, it looks easiest to get the x term by itself here. To get the x term by itself, I'll move the 2y to the other side. Actually, it's a -2y. So when I do that, what equation do I get for x?
X equals -12 plus 2y.
All right, -12 plus 2y. I'm going to write it in slightly different order. 2y minus 12, but the same thing. Now that you've got a value for x, or an expression for x, you're going to take that expression and substitute it into the other equation. So let's take that and plug it in here for x. So how's that going to work out? Well, it's going to be 3 times 2y minus 12. We're replacing that expression for x with 2y minus 12 plus y equals -22. Now notice all we did was just replace that x by this expression here. That's going to give me 6y minus 36 plus y equals -22. If I combine like terms on the left-hand side, I get 7y minus 36 equals -22. Let's add 36 to both sides. What's that going to give me? What equation pops out?
14.
Yep.
7y
7y equals
equals 14.
14, so y equals 2. Please keep in mind you're only half done. Well, maybe not quite half done, a little bit more than half done, but what else do you think I might want?
Well, x value.
Yeah, find the x value, all right? Now you got 3 choices as to where you can find the x value. This equation, or this one. Since I've already got x solved for, I'd probably go for that one. So if I plug in y equals 2, 2 times 2 is 4, 4 minus 12 is -8. So x equals -8. Nice. Overall, you'll probably be asked to write your solution in terms of coordinates, so -8 and 2 is what you'll probably end up typing into WebAssign. So that's solving something by substitution. But what else could I do? Well, we're not going to get to the answer to all those possibilities just today, but there is one other way that you can work on this, and that's with the addition method. A lot of times I think WebAssign will call it the elimination method. I don't know. Just not really happy with the term there, elimination. So let's take a look at example D with addition. So example D. And the idea behind example D is this. Just like the example D by substitution, I got rid of one of the variables. I'm going to try and get rid of one of the variables here. 3x plus y equals negative 22. X minus 2y equals negative 12. What you can do is you can add a multiple of one equation to another equation. So I notice that I've got a negative 2y here. What do I have to add to a negative 2y in order to cancel it out? Plus 2y. So let's just multiply this equation by 2. And that's going to give me 6x plus 2y equals negative 44. And I'm going to add that to x minus 2y equals negative 12. Great. Nikki, question or just?
No, just
Okay, that's fine. What do I get when I add these together?
7x and then 56.
Yeah, 7x equals negative 56. Wow, so that means x equals negative 8. Great. That's one out of two of the coordinate pair that you need. But how am I going to find y? Yes.
You just plug x back into one of the equations.
Plug x back into one of the original equations. Sure. Does it matter which one?
No.
No. Which one looks easier?
The bottom one.
Bottom one? All right, let's do the bottom one. So it'll be negative 8 minus 2y equals negative 12. Add 8 to both sides. End up with negative 2y equals negative 4, or y equals 2. Beautiful. There's your solution. Negative 8 and 2.
Does this mean that you can add any true statement to another statement, as long as it's consistently applied on both sides, and remove any terms you want?
You can add any multiple of this equation to this equation, or vice versa. Or you can multiply both of them. In fact, on one of the problems that I'm going to let you work on, you will have to multiply like both equations in order to solve, in order to get one of these to cancel each other out.
I mean, like, in a larger sense. So
Mm,
if you have hairy variables, for instance, or nasty constants to deal with.
if you have nasty constants to deal with, I'd probably work on a couple different methods. I'm not sure I'd use, something by hand like this. I'd use either inverse matrices or Gaussian elimination. Those are things that we're going to cover later in chapter 10. So some of those ideas are getting a little bit ahead of us. Kramer's rule is an option, but it's not my favorite option by far. All right, let's flip things over.
I have a question.
Yeah.
This is what you're saying, but why did you multiply the top of the equation?
Notice what happened here. 2y and negative 2y. What happens when I add those two together?
So would cancel.
They add to a 0. And so what you want to do when you're working with these things is manipulate your equations by multiplying one, the other, or both so that you get a variable to cancel itself out. So that's the idea behind elimination, and I appreciate that. We'll do another example with the elimination method, but we have to clean things up a little bit first. So let's take a look at example E here. Most of you would probably be less than happy. In fact, I see a couple long faces like, oh man, fractions. Not happy with fractions. Yes, sir?
Multiply by 14 at the beginning.
Ah, well done. So the idea is to get rid of the fractions right away, right? I mean, why spend your time working with them? So I'll multiply by 14 here. How about the second equation? What should I multiply there? 14. Multiply both of them by 14. Now, if you struggle with fractions, if you're like, oh my gosh, they're not so user-friendly for you, that's okay. Let's just take out our calculators and look what our calculator can do for us if you needed to. Now, I'm not going to be looking over your shoulder. There's no shame in taking out your calculator if you want to make sure that you get this right. But that 14 has to distribute itself to all three parts of this equation, including the 3, even though there's no fraction there. So let's just take 14 times 2 divided by 7. And if you don't feel like doing this in your head, that's fine. Just do it on your calculator and get the right answer. I don't want to see you get these problems wrong because you made an arithmetic error. So we get a 4 here. And then 14 times 1/14. Well, I hope we can do that one in our head. Multiply a number by its reciprocal, you're going to get a 1. So 4x plus y equals 14 times 3 is going to be 42. Try and clean up the numerator, or the first equation. Elizabeth, what do we get for the top equation after we multiply everything through by 14?
Negative 3x minus y equals negative 14.
Perfect, perfect. So this one you could do by addition or substitution, but what does it look like it's easiest to do? What looks like the path of least resistance? Yeah. So the addition or elimination, because when we add these two equations together, what nice thing happens? Yeah, the y cancels out. Thank you, Alex. So the y cancels itself out. I get 2x equals 28. Wow, that's pretty nice. Divide by 2 on both sides, so what does x equal? X equals 14. Halfway done. Now personally, I'd probably put it into the bottom equation, just me, but you're welcome to plug it into whatever equation works for you. So 4 times 14 plus y equals 42. That's 56. If I subtract 56 from both sides, then I end up with y equals negative 14. And I'm fine with it on a test if you just circle both answers like that. I'm happier if you write it as 14 and negative 14. That's probably the way you're going to be asked to write it in WebAssign. But just make sure that you give me both answers, x and y. Okay. All right, let's keep going. Example F. I helped you out in example E. Got you out of a jam because we cleared up all the fractions. What would you do in example F? How can we make this a little bit more reasonable to deal with?
Well, you could multiply either one by, well, the goal is to get two of these like things, like the x and y values to be the same.
Mm-hmm.
The cancellation around.
Multiply by 10.
Yeah,
By 10,
just
right?
to start with, I'd multiply by 10 just to get rid of the decimals.
But
Yeah.
it could be like either, you could like cancel either x or y, right?
Yes, you can cancel out x or y.
Okay.
So I'll multiply the top one by 10, and how about the bottom one by 10 as well? So if I multiply the top one by 10, what's that going to give me? What equation pops out of it if I multiply the top one by 10? 2x minus 2y equals negative 34. Great. And then someone else for the bottom one? Nice. Negative 3x plus 5y equals 69. Now to solve this, there's a couple things you could do. You could multiply, say, the top equation by 3 and the bottom equation by 2, and then both of these would have a 6 and a negative 6 as a coefficient. That would get rid of the x's. You could do likewise to get rid of the y's. You could multiply the top one by 5 and the bottom one by 2, then you'd have negative 10 and 10, and again, you could solve that by elimination. But I'm going to let you solve that one yourself in groups in a little bit. Let's instead turn our attention to example G here. So, for example G, yeah, man, those numbers just aren't looking very user-friendly, are they?
Nope.
Yeah, I see a little scowl from the back, like, ew, that looks pretty unhealthy. Is there anything I could do here to make my life easier? Ellie?
On the bottom equation, you could divide by 11.
Nice. Let's divide everything by 11 in the bottom equation. So, Zaid, what if I divide everything by 11? What equation will I get?
Negative x equals 4y equals negative 5.
Perfect. Nice.
Top one by 25 as well.
All right, and then we'll divide the top one by 25. Now, everything has to get divided by 25, and everything gets divided by 11. Michael, you gave this one to me, so you get the honors. What does that equal over here?
Top one,
Yep,
would that be x minus 4 equals 5?
x minus 4y equals 5. Nice. Something interesting is happening here. How would you solve this one? Addition, substitution? Any suggestions?
They're the same.
When you add these together, something interesting happens. What equation do I get when I add these together? 0 equals what? 0. 0 equals 0.
The
Woohoo!
name is in all, not the exact name you have it.
The thing that I want to point out here is that even though it's kind of silly, 0 equals 0 is true, right? That's a true system, that's a true statement. It's silly, it's trivial, but 0 does equal 0. So, what's that saying about my system of equations?
Consistent, dependent.
Yeah, not quite all real numbers, but it's saying that there's an infinite number of solutions. So if we go back to this handout, which I didn't give you, really what it's saying is you've got something like this. What do we call a system of equations like this, or how do we characterize it? Is this consistent or inconsistent? Consistent because the lines overlap, there's an infinite number of solutions. Consistent. But there's something else that I said about this. It's dependent. And if you have something like 0 equals 0, or a true statement, or any true statement, after the variables have dropped out, then that implies that you have a dependent system of equations. So if the variables drop out and you end up with something true, you've got a dependent system of equations. Okay, let's look at some other things here. Sometimes I put equations or problems on a test where I say, well, it doesn't quite work in this case, where I say solve by graphing without graphing. But let's see what we can do with this one. If you were to plug this into your graphing calculator and want to graph it, you'd have to solve for y. You'd have to get y by itself. So what's that going to look like here? Well, that's going to be, let's see. That's not where I'm going with this, though. So if I were to solve for y, I'd probably move the 3y to the right side and the 2 to the left-hand side. That's going to change up signs, and I'll end up with 2x plus 2 equals 3y. Not quite done solving for y. What do I have to do to solve for y?
Divide both sides by 3.
Divide both sides by 3. So I get 2x plus 2 over 3 equals y. I could do likewise for this one. why don't you try yourself to see if you can't put it in a similar form. If you're watching this later, pause the video, see if you can't figure out how to move things around to get y by itself. Okay, let's look at this one. Personally, I would start by interchanging 21y and the 9, so switch those around. So I would start by rewriting that as 14x minus 9 equals 21y. What do I have to do to finish solving for y? Yeah, divide both sides by 21. So 14x minus 9 divided by 21 equals y. And now you can plug these things into your graphing calculator. Your graphing calculator is not quite like Desmos. You actually have to solve for y before you plug those things in. So there's a couple ways we can plug those in. I'll show you one of each. So for the first one, I'm just going to use parentheses like this. Parenthesis 2x plus 2 divided by 3. And for the second one, let's do this. Let's get a little bit fancy. Instead of using parentheses like that, I'm going to hit the alpha key, and then I think is it under the format?
It's under y equals.
Well, I know it's under the y equals key, but I know this is another place you can get it. Is it alpha window?
Well, it's like.
No, that's not.
It's
It's-
alpha.
Yeah, let's just go here. Alpha y equals.
I think there's another way you can do it.
There is another
without
place.
E somehow, but
Yeah. So anyways, 14x minus 9 divided by 21.
oh, it's math, and then you have to arrow all the way over to the
Yeah.
action.
Now let's set up our graph. I don't really know where to graph this thing because I haven't thought about this much. So do you remember the kind of catch-all for how to graph this, you know, a good first place to start?
Zoom 6.
Zoom 6, good. So it's going to be Zoom 0 or Zoom Standard. Zoom 6. What are you seeing?
parallel.
Parallel lines. So is this system consistent or inconsistent? Consistent. Dependent or independent? Independent. Nice. So inconsistent, independent. Inconsistent, independent. These are two names and terms that I want you to be able to use. Let's go back here for just a moment to example G and remind ourselves of how to write this general solution in terms of x. So the solution to this system of equations is really just some pair of numbers x and y. But I want to characterize y. I want to write y as something. So let's take a look at this equation right here. Let's solve for y in this equation. So let's move the 4y to the right-hand side and the 5 to the left-hand side. Can anyone see an advantage of doing that? Why would I move the 4y to the right-hand side? What nice thing happens when it moves from left to right? It changes the sign to positive. It's giving yourself less of a chance to make a mistake. So that's x minus 5 equals 4y. How would you write that in terms of y then? What's y equal?
X minus 5 over 4.
X minus 5 over 4 equals y. Looking good there. So your solution, instead of writing it as an x and y, you could write it as x and x minus 5 over 4. Those are the general pair of points that you would write as you're working through a system of equations like this, or that you could get. So you're parameterizing the solution there. Let's take a look at that graphically. Let me get rid of something else, and then bring the graph back. So back over to here. So you can see that the two graphs are the same, here and here. Let me put this point on there, and anything of this form is going to be on that line for different values of A. And you can kind of zoom around as much as you want, and you're always going to be on this line. So you've got this nice parametric version of the equation of the line. So nice. An infinite number of solutions, but at least you've kind of characterized them somehow. One last thing to discuss here, and I think, unless you're an unusual class, that somebody out there has probably played, I don't know, Minecraft before? Yeah? All right. So let's apply some of our math to something very practical, like finding your stronghold in Minecraft, which, you know, is on everyone's agenda. Let's see. Where is it? So if you look up on the internet, you'll find tons of ways, tons of websites and YouTube videos about calculating where your stronghold is in Minecraft. We're not going to do it with trigonometry because that's not this course, but we can do it other ways. So the nice thing about Minecraft is that if you're trying to find this location of the stronghold, you can take out your compass and it will point you in the right direction. So let's say you're down here and you want to find your stronghold, so take a compass reading, it says, yeah, in this direction. Then you move a little ways to another spot and find a compass direction or a compass heading from another spot. And both of those 2 points give you a line, so let me give you the equation of those lines. Here's one, here's the other. Let's make that a little bit more impressive. There we go. So what we want to do is we want to find where these two lines cross each other. Now to make this actually something practical, we're going to locate this using our calculators. So take out your calculator and let's plug in those two equations. So those two equations are right here and here. So I'll hit the y equals key and clear out the stuff that was there. The first equation I'm going to plug in is negative 0.7x minus 3.4. And then 0.5x for the other equation. Do I have a good enough viewing window? I don't know. We'll take a look. I'll give you a second to get those equations in there. We're just going to use the viewing window we had before. If we need to make adjustments, we will. I think we should probably be able to see where it intersects. Hit the graph key, and yeah, we've got a point of intersection there. So to remind you how to find those points of intersection, let's go to the Calculate menu. So let's clear this out here. Second, Trace. I want to find the intersection. We've done this before, but it doesn't hurt to review it. Get close to your point of intersection, and then press enter how many times?
3.
3, yeah, 3 times. One for the first curve, one for the second curve, and one just for good luck. And bam, there you go. So negative 2.8333, that'd be -2 and 5, 6. And I don't quite recognize the other one off the top of my head, but
Would it be like negative 1.4 and like a third?
I'm trying to think. 4. That's negative. Let's see. You got me curious now. So negative 1.4. Let's write that as 7/5, and then plus 1 divided by 60. There we go. So let's hit the math key. 17/12. Ah, silly me, I didn't know that one. All right, comments or thoughts on that last one there? Yes?
So for problems like question H, our final answer would be the inconsistent, independent.
Correct. H, the last thing you'd write is consistent, inconsistent, independent.
Okay.
Yes. Antonio?
Going off of you saying that, what about the map of Earth? How did they figure all that stuff out?
That's a lot different. You need spherical coordinates for that because the Earth has some curvature to it. We're just assuming that this is exactly flat land. There's no z values to this at all. It's completely flat. So yeah, it's a great question. Some of those early cartographers, hats off to them. Yeah. All right, cool. Let's see. Let's yeah. Let's call it a day in this section.